Welcome to Breadboarding. In the previous video, we managed to set up an ISA bus connector down the bottom here with the socket. We've plugged in an 8-bit VGA card into here, and we managed to actually get it working with a test pattern here. But in order to get this working, we had to copy the video BIOS into main RAM and run the video BIOS from RAM. And then we just used one of the test programs we used previously to get this test pattern. So in this video, what we're going to try and do is to now get this working with the boot up process with the BIOS and see if we can actually run MS-DOS with the VGA card. This is video 22 in the Breadboard PC 8088 version 2, and this is the VGA video controller part 2. So I was looking into the background to the ISA bus. This was the original interface used for expansion cards when the original IBM PC and PCXT came out in 1981 and 1983, and this was then extended with the PCAT to become a 16-bit bus, and this was also used in the early 386s. This documentation comes from the Compact Despro 386. What this indicates is when memory reads, memory writes, and IO reads and IO writes are running on the bus in 8-bit mode over the ISA bus, then in fact, by default, it's actually got quite a large number of wait states. Now, up till now, because we've been using fairly modern chips, so the RAM is static RAM and the ROMs are fairly fast, then we haven't needed to include really any wait states as such. And so to have this number of wait states here, this is up to potentially almost about 1.5 milliseconds, 12 wait states at the 8 megahertz clock that they're talking about here. So I started to look into this, and you can see over here there's a few bits that says the standard 8-bit ISA bus has 4 wait states unless the 0 wait state is activated, and the default 8-bit read time with its 4 wait states is sufficient for interfacing even slow ROMs to the ISA bus. So what I was thinking is perhaps the ROM chips on this VGA card are quite slow, and if we're trying to read them too quickly, that might be causing the problem. Now, at the moment, we're only using the 8-bit bus. We're not dealing with the 16-bit bus. So this bit in orange here, if we're actually expanding this perhaps to work with the 386 in the future, we might want to consider this 0 wait state option. But at the moment, I'm not going to bother with that. And all this does down here is just reproducing some of this information. So given that our bus is in fact running close to 8 megahertz, then in fact the default read and write times is about 250 nanoseconds, slightly less than that in fact, and therefore we need to add these wait states to increase the cycle time. And this little bit down the bottom here shows that if we're in 8-bit mode, then really you should have a read cycle time of about 750 nanoseconds or more. And at the moment, when we're running in normal mode at 4.77 megahertz, then we've got about 400 nanoseconds, and when we're running in turbo mode, the read time's close to about 250 nanoseconds. So this is most likely to be part of the problem. I also had some problems. The problem that we solved in the previous video, when reading the video BIOS from the standard location, so this is in the C0000 segment, and it's about 32K, sometimes it would actually fail the checksum. And when I was looking at it in the logic analyzer, you can see down the bottom here, so you can see that when reading the ROM at 7FC7, we're actually reading 4.6, and also reading 4.6 there as well, and 4.6. Now it just so happens that the code that's actually reading the byte here then is followed by 4.6E2, and sometimes I was seeing 4.6, other times I was seeing E2. Now in fact, if we look at the area of the ROM and that particular region down the end, so about the last sort of 180 or so bytes is all 0. So when we're at that sort of part of the ROM, we would expect to be reading 0. So the fact that we're not indicates that there was some sort of problem there. Now that was largely worked around by loading the BIOS in S-record format into the RAM, and we were able to run it in RAM. But the other problem then was that even when that checksum passed, then when it was actually getting to a certain bit of memory, it did a call to jump, which just had a C3 return on it. But when it actually returned from that, the memory accesses were getting corrupted. It was reproducible on a regular basis, and it really prevented the video BIOS from completing. Now, obviously, when we used our monitor to save the ROM into memory and run it from there, then it was working okay. That was in the previous video 21, for which there will be a link up the top here. So when we loaded the video BIOS into a lower memory segment and then we ran it, then that was working. So I suspect it might be an issue with the VGA card and in particular the video ROM. Unfortunately, I don't have a PC with an ISA bus that I can test this on, so I'm not able to really independently test this card. But if you just have a look at this, is showing where the particular problem occurred. So you'll see that when we're reading these particular instructions, we'd expect to have on FFA BA C203, and when we look over here, you can see that we're reading the BA, but then when we'd expect the C2, we're not getting that, and then we're just jumping straight to 03, and that's enough to mess things up so that the video BIOS wouldn't run. So again, that would indicate that despite it actually reading through quite a bit of the ROM, from time to time we're actually getting these sorts of corruptions from reading the ROM. It could very well have been caused by these bus timings that I've been talking about. So how are we going to fix it? Well, to start with, I have ordered another ISA Bus VGA card, the same as what I've already got. So that should hopefully arrive in the next week or so, and at least I'll be able to then verify whether or not it's a problem with my setup, whether or not it's a video card specific issue. But in the meantime, what I've done is I've actually now changed the BIOS, the main PC BIOS, to shadow the VGA BIOS to unused RAM in the upper memory area. Now at the moment, the Breadboard PC has two 512k RAMs. However, the second RAM has only got 128k maps, so that gives us our 640k. However, there is about 192k unused upper memory in the C8000 to F7FFF. So this is just below the BIOS ROM and above all of the VGA memory and VGA BIOS. So what I've done is I've modified the decoder chip so that now this area of memory is now available, so we can use this as upper memory. And I've modified the standard XI8088 BIOS. The BIOS extension scan is now been changed that when it's calculating the checksum, it will also then move the bytes to a segment higher, so it'll actually be on the D8000 range. I haven't made these configurable options in the BIOS setup for Shadow RAM. I've just hard coded this for the moment. The checksum still fails. It will log it to post as a code 13. I was looking at whether I would repeat it a number of times until success, but it's actually been reliable enough that I haven't really needed to do that. And the only real difference now is that when we call the video BIOS, it now uses this adjusted segment. So it was using C000 previously, and now it's going to be using the D00, and this is in the video RAM. And I've also added the wait states for the ISA bus memory and I/O access. Now, when I did these changes originally, I did it for all ROM and all RAM access. However, because it slows down the rest of the computer quite a bit, and even the startup Intel type sound at the beginning of the beeps is actually quite a bit slower. So what I've done is I've modified this now so that it only runs the ISA bus accesses for RAM and ROM at the slower speeds, and generally all I/O accesses will also be at these slower speeds. So this just shows the Breadboard PC memory map. So in the first 1K, we've got the interrupt vectors, which is a pretty much standard Intel 8088, 8086. And then the BIOS data area is where a lot of the key BIOS data is stored. The default stack for the BIOS actually starts at the top of the interrupt vector area and works downwards. So if we ever see memory access in the 300 to 3FF range, that generally means we're talking about the stack in the BIOS. You can see here that the main system RAM goes all the way from start of the address space all the way up to 9FFFF. That's just below A0000. And the A0000 to the C7FFF, this is where the monochrome display adapter, CGA and VGA video RAM and the VGA video BIOS is. So above this area now, this is the unused upper memory area. And so what I've now done is modified the address decoder for the second RAM chip to also now map in this area as well. So this is now available to write to, and then the BIOS and monitor is in the top 32K of EPROM there. So what we're going to be doing is modifying the address decoder so that we've got access to this extra RAM here, and we'll then also modify the BIOS to copy the VGA video BIOS up into this area and then to execute it from here. So first of all, just look at the changes to the address decoder. So this is the main address decoder, and you can see there's a few changes that we've had to make here. So version 3 has been updated for video 22 to add upper memory to RAM 1 chip. And what I've also done is change the CGA RAM chip enable to external memory, and this basically provides a signal to the ready wait logic so that it knows when it's accessing the ISA bus so that we can slow down memory accesses for the ISA bus. And you'll see that the CGA RAM's been changed to external memory. And the pins changed as well. So now the external memory is in the address range A0000 to C7FF. So this is where the VGA card basically is located. And then you can also see down the bottom here that our second chip enable for the RAM has now included this additional area, so above where the video card is, all the way up to the bottom of the BIOS EPROM. So those changes have been programmed, compiled and programmed. Then the other change is the shadowing of the VGA BIOS to upper memory. Now this slide is similar to one of the ones I covered in the previous video, and this is basically covering what the BIOS does. It scans the region of C0000 to C8000, looking for this AA55 magic number. And it still does this, but the only difference is now is that as it reads all the bytes, it also writes them to the D0000 range and continues to calculate the checksum. If the checksum's wrong, rather than just carrying on and ignoring it and looking for some more, it does output a 13 postcode, so we can tell when the checksum has failed. The sum is 0, then the third byte is the short jump to execute. So basically what we then do is to write the offset of 3, and the segment is now, rather than C000, it's now D000, and that goes to the BIOS data area, where then the BIOS does the far jump. So what it now does is it executes the VGA BIOS from RAM rather than from ROM, and that seems to have increased stability, and then it still skips the built-in MDA CGA BIOS initialization as well. So this is the code that's been changed. This is the standard extension scan. Now this is actually also used for looking at other card extensions. So if you had a network card or additional I/O cards that had ROMs on them, then this would also be used for that. But I've just commented out the bits for the extension ROMs for the moment. And basically what this does now is slightly changed from what we had previously. But now what we do, once we've added the byte that we've read to the checksum, what we now also do is to copy it into this other range. So the destination index here is now being used. And so basically we just increment the source index and destination index. And because the extra segment is now set to the C000 plus 1000. So in fact, it will relocate it. So it's a bit of a hack for the moment. Theoretically, if the ROM was working off the video card properly, then we wouldn't need this. So hopefully at some point I'll be able to reverse this out when I get the second card. But this just means that I'm able to get the video BIOS to initialize properly. So a few other issues I also had to address. So during the development of this ROM shadowing, I was using this move SB. Now, this didn't work, unfortunately, because the time between the read and the write was uncontrollable and was a bit too quick, and it was causing a number of problems and resulted in this sort of screen down the bottom. And I was looking at the different timings between the various sections. And what I did is the code that you've just seen was the compromise. So then what about the wait states and the VGA BIOS, video RAM and the floppy disk controller? So the main system RAM and ROM is modern with a 55 nanosecond access time, so no need for wait states there. But the ISA bus should have 750 nanosecond access time, so that's at least 4 wait states. Now, with 8 megahertz and 0 wait states. That will be 1 wait state, but we're not going to worry about this 0 wait state for the moment. So I did some checks to see whether Video BIOS ROM required 4 wait states, 2 wait states, or 1 wait state, and generally it required this 4 wait states even when things were running at the normal frequency and not at the turbo. There was also, when looking at it, there is a bus ready signal that the video card produces, which is to add additional wait states. However, it looked a bit erratic, and some of these bus ready signals were only 30 or 40 nanoseconds wide. So I didn't have great confidence that this bus ready was actually going to solve problems. So that's something to look at with the second video card. Now, floppy disk access may be too slow with these 4 wait states. That's something I'll have to check, but it looks like it's actually okay. So I've removed some of the no operation codes I had in the floppy disk code previously, because now the disk accesses are taking a bit longer, and so some of these timing issues have gone. And I've used this external memory output pin from the decoder that basically enables me to only enable the wait states for RAM and ROM on the ISA VGA card. I've also done some testing, and the turbo mode does actually need some more wait states, so I've actually increased the wait states up to about 7 for when we're in the turbo mode. So if you just have a look at the changes necessary to the PLD for that. So this is the speaker ready wait PLD, and you can see that there have been a couple of changes I did. I didn't really cover these changes from the previous video, but between this video and the last video there have been a number of changes. There are a couple of issues. I mislabeled the IO read and IO write were the wrong way around, not that it mattered too much. And then we've added a few other clocks. So this is a clock signal generated from the IO read, IO write, and in fact the memory read and memory write now. We've also now added the memory read and memory write have now been added as well, so we're able to determine what wait states to do for these as well, and also the external memory and the turbo input. So this now means that our delays, the ready wait delays, we either use the ready wait delay of 4 when we're not in turbo mode, or the ready wait of 7 when we are in turbo mode. So this has taken quite a while to get to the bottom of. And because this is an ATF 750C, we've actually got some additional pin nodes. So this is some of the internal gates that we can access. And this basically shows that our clock signal that is used for generating the wait states is based on the IO read, IO write, the memory read when we've got external memory, or the memory write when external memory. And this means when we're using the system RAM and the BIOS ROM at the end, then these don't require wait states. And because now that the original logic from here is in the KeyCAD diagram, and it came from the original PCXT, now this has been modified, and because we've now got turbo mode and standard mode, then the ready wait reset needs to be based on either when we're not in turbo mode, we reset the ready waits on 4 cycles, and when it's in turbo, then we do it on 7 cycles. So these changes here have actually allowed the ready wait states to now be extended to 7 cycles in turbo mode and 4 in standard mode. And there was another problem that I did run into when doing that. What I was finding is that the first read and write would actually get extended, but the second read or write occurring afterwards would end up actually with the default wait state here. So this would be about 750, but this one we're going back to the default about 200. So one of the problems here that I've shown you in that the ready wait asynchronous reset needed to have some logic changes and things. So it's taken a little while to sort out, but now it is actually at least booting the video BIOS, and I'm able to get the video output. So what I'm going to do now is to start up the Breadboard PC, and we'll hopefully now be able to boot up the BIOS and get to the command prompt. So I'm able to do a directory and also type out autoexec.bat. There's nothing else on the disk, so that's as good as we get here. Now the only issue with this is that there are some problems still with the video timing, and that if I scroll this then the screen does still get messed up. So I'm hoping that the second video card that I've ordered will sort this out. If it doesn't, then I'll have to go back and have a look at the memory timing again. So there we have it. So I managed to get the video BIOS now booting up with the rest of the PC and MS-DOS. We're able to get DOS up and running and at least get some keyboard input there. So I'm going to be having another look at this when the next video card arrives and see whether or not it's a problem with my video card or whether it's a problem with the setup itself. So if you don't want to miss out on future videos, then please hit subscribe, and if you found it interesting, please hit like. It just helps to make the videos available to more people. Thanks for watching.